The purpose of this lab is to analyze differences between the motion of an observed object and a model in which the object's velocity is constant. We will apply Newton's first and second laws to explain the motion of this film canister as it moves across a table. Due to Newton's first law, when velocity is constant, force is zero, which we assumed as true in our model. Here's the video of the film canister moving across the screen. We start recording data after my hand leaves the film canister, so we eliminate acceleration caused by the hand. The origin of the system is 3 centimeters left of the center of mass of the film at t equals 0. The positive side of the x-axis points right, so the canister moves in the negative direction. Measurements were calibrated to the diameter of the canister, which was 3.25 centimeters. We used the first 2 points from our data to create the initial velocity for our model. Our result was a velocity vector with components negative 0.394, 0, and 0. For our model, we assume the film canister has a velocity vector in which only the x component has a value which is not 0, and this is not true in real life, as we'll later discuss. For our model, we'll assume force of friction equals 0, and we'll set F net to a vector with 3 components equaling 0, as shown right here. Though our code uses Newton's second law in the form ball.vel plus equals ball.vel plus Fnet over ball.m times delta t, through Newton's first law, we know Fnet has components 0, 0, and 0. Next, here's our graph. It's clear observed and predicted motions are similar, and because I used a smooth table, force of friction probably did not detract too much from the results. We can assume net force is about 0 because push from the table and pull from gravity cancel out, and pull from friction is small. 2 pushes and pulls, gravity and push from table, make Fnet in the y direction 0, and the small force of friction seems negligible, which allows Fnet in the x direction to be about equal to 0. With constant velocity in our model, we observe a position versus time graph where position increases linearly since x initial plus vt equals x final, and both x initial and velocity v are constants. However, there are some differences between the observed and predicted data too. When we watch the video, going back to tracker, you'll notice that at first the canister moves toward us, causing us to underestimate the initial speed. The canister later straightens back up, which is why we get an underestimation of position after t equals 0.2 in the graph. You can see that the displacement from the origin is greater than the model position in our experimental position after t equals 0.2. Notice how the blue dots are further down than the red line. And that concludes the lab report, and the conclusions we can make are that there are other factors that influenced our data, like the curvature of the canister as it moved across the table, and we can probably assume, based on the similarity of the experimental and model positions, that force of friction was very close to negligible.